objective, let me find it here. Okay, we should be at this objective here. We'll see how far we can get in, well, let's say 20 minutes. I'll try to keep to a 20-minute video. Alright, so this objective. Given the equation for a function, graph the function and its numerical derivative function on the same set of axes, and make statements about the relationships between the derivative function and the original function. Well, first of all, let's talk about this little phrase here. That means estimate. So numerical derivative is the estimation of the derivative, but refers to the graphical estimation. Okay, so graphing calculators calculate numerical derivatives by using difference quotients, just like you did in the last section. Okay, so you'll see the forward, backward, symmetric. It's just using different x values. So forward is you use a value that's just to the right of the value you're looking for. Backward, you use the value directly to the left of the value you're looking for. Symmetric is you use the in front value and the behind value and not the actual value. As you might guess from the above answers, the actual value of the derivative is actually 12. And then we're going to show how the numerical derivative here will calculate it. So, taking your graphing calculators. And I didn't spend a lot of time on these graphs. These graphs just represent finding the tangent line or the slope of the curve, the estimation, using, 3 different types of values. And your calculator does the same thing, basically, by calculating all 3 and then punching out a number that gives you an estimation of the derivative. That doesn't mean that this is the instantaneous rate of change necessarily, but it's a good estimation because the calculator does these quotients for you. So they're not instantaneous because you're still having to find the difference between 2 different x values, but it's pretty close. Okay, so in your calculator to estimate, you're going to go to your math button. There we go. So you're going to go to the math button, and then you go down to where it says NDeriv. You select it, and then it's going to go math. You want the NDeriv, and then the input is you put the function, you put your independent variable, which is x, and then you put the c value or the specific x that you want. Like up here it would have been at 2 that we want to find the value of the derivative. This estimates the derivative. Again, this function on your calculator does this for you, so you don't have to do it all over. So an example of this that we're going to do, to put it in, is NDeriv. You're going to take the function x cubed, your independent variable is x, and the value we're plugging in is 2. And that represents this up here. So let's look and see what happens. So if you put in x cubed, then you put a comma, and then x, your independent variable, and then comma again, and then the value we want, it gives you 12. Now you might have other decimals in there, but we're just going to say 12 is a good estimate here. So your calculator, again, did the difference quotient for you, or I shouldn't say the difference quotient, well, difference quotient, not the limit of the difference quotient, but just the difference quotient, like it's shown here, and punched out the value that you would get if you did it by hand, all 3 ways. Alright, because there is a value of the derivative for each value of x, or you could think of it as an instantaneous rate of change for any given value x, or you can think of it at any given time for a function, or any given x, you might be going at a different speed at every single x value. But because there's a value of the derivative for each value of x, then there is a function whose independent variable is x, and whose dependent variable is the value of the derivative. This function is called the derivative function, for lack of a better term. And it's usually abbreviated by one of the following. Okay, so all this is saying is that there is a function that exists that if you plugged in 2, you would get out 12. Other than the difference quotient up here, there is an actual derivative function that where you plug in 2, you're going to get 12. And so the rest of this unit is working with the derivative specifically and working with those derivative functions, because this function will give the value of the derivative at any point. We've kind of already talked about this with the limit process that we were working in last objective. But this is where our focus is going to be for this unit, is working with these derivative functions. So let's talk about the labels. So you'll see it as f prime of x. That's how you would read that. F prime of x. You'll see it in what's called Leibniz notation, which is dy over dx. You'll see it as y prime. So whenever you see f prime of x, that's referring to a function that is the derivative. So you'd put in an x value, and the output of that function would be the instantaneous rate of change. We could have labeled, if you think back to the last unit, when we were making r of x's that represented the average rate of change, that we could have labeled f prime because it represented the derivative. Okay, we will use the numeric derivative instruction from above to graph the derivative on the same coordinate plane as your original function and then compare how they look in relation to another. Okay, so to graph the derivative function, this is what you would put into your calculator. In y1, you put your function. In y sub 2, you would put n deriv y sub 1, comma, x. And this estimates the derivative of f of x at any x value. Okay, so we're going to end up with two graphs, one graph being our original function, and then the next graph, basically the calculator is going to be calculating all the different derivative values. So, like it's going to take the 2 and calculate the 12, and it's going to take 2.01 and calculate the derivative at that point. So you'll notice that when we graph the derivative, or when that second graph comes up, it actually goes a lot slower because the calculator is having to do a lot of work to get up on the screen because it's doing a bunch of estimation. Okay, so we're going to flip to the next page here. The first function that we're going to use is x cubed minus 5x squared minus 8x plus 70. Okay, the first thing that we do is we're going to plot the graphs of f and f prime, the numerical derivative of f, on the same set of axes and sketch below. Okay, so I'm going to keep hammering this a little bit, but what does the numerical derivative of f mean? This means it's a function, or in this case, a graph, that shows the values of the rates of change. Okay, so in essence, your graph, all the y values actually represent velocities, or speeds, or rates of change. So when we graph the derivative, and we, let's say, picked a point off the derivative graph, that y value actually represents the speed at that x value. Alright, so in y sub 1, we're going to put x cubed minus 5x squared minus 8x plus 70. In y sub 2, in our calculator, we're going to put n deriv y1, comma, x. Okay, and then actually I'm going to redraw my axes here. And I'm going to give you, for sake of time, the window that you would want to use. So -2 to 10. And then 100 to -20. Okay, so here we go. And y equals y1. You're going to put x cubed minus 5x squared minus 8x plus 70. Then in y sub 2, you're going to put and derive. Now to get the y sub 1 in there, you go to the vars menu. And then you go to y-vars, function, and there's your y1. Then you do comma x, okay, because this is saying the independent variable is x, and then we want to evaluate it at every x, not just a specific x. And then we're going to actually change this. Let's change this to a more solid graph so we can see the one that graphs as the derivative. And then we're going to go to window. I'm going to set my window parameters like I said there. So -2 to 10, and -20 to 100. Okay, and then I'm going to hit graph. Whoops. Okay, so this is the original function that's graphed, which it should look like that because it's a cubic. And then here's my derivative graph. So notice how slowly it's graphing there? That's because for every single x value, your calculator is having to calculate the derivative using those symmetric quotients. Okay, so as best you can, I want you maybe to pause the video and sketch this on your paper. I'm going to do the best job I can here. So, okay, so it's very rough, but you kind of get the idea. Alright, let's label these functions. This is f of x, this is f prime of x. Now, this objective is referring to, I believe it's standard D3, where it talks about comparing derivatives in the original graph. The more connections you can make between the derivative graph and the original graph, the better and better you're going to understand derivatives and the part they play not only in calculus and in math, but just in the world, like what they represent in terms of real-life situations. Okay, so we're going to kind of dissect each one of these. Function f is called a cubic function. What type of function does f prime appear to be? Okay, so hopefully you can recognize that f prime appears to be quadratic. Okay, we're going to trace to find values of f of 3 and f prime of 3. Alright, so I'm going to hit trace. I'm going to go to where x is 3, or almost 3. Now, by scrolling over to 3, I'm on function f of x. You can see that function f of x has, well, almost at 3 has a y value. Excuse me, around 28. It's positive. And then if I hit the down, it's going to jump down to the f prime. You can see it's the same x value, but now my derivative value is negative. Okay, so if we were to actually plug in 3, you would get 28. We just had an estimate because my calculator couldn't get exactly 23. If we were to plug 3 into your derivative function, which I know we don't have technically yet, you would get close to -11. You can kind of see that there. You're really close to 3, really close to -11. So just in general, at f prime 3, we can say, well, f prime 3 is a negative value. And then remember, derivatives or the value of a derivative is velocity, basically. So when you have a negative velocity, what does that tell you about your original graph? Well, you can see if I have a negative velocity, a negative value for the velocity, my original graph is actually decreasing. Okay, so we can say that f prime 3 is negative where f(x) is decreasing. Okay. The next thing that we're going to kind of dissect about these two graphs is for what values of x does f prime of x appear to be 0? So when we look at our graph, it appears to be 0, and we're looking at f prime here. It appears to be 0 at 4 and at maybe negative 0.5-ish. So let's actually find those. F prime of x is 0 for at x equals 4. And I'll tell you that this isn't 0.5, but it's negative 0.7. So at 4 and at x equals negative 0.7. Okay. Now, what's happening here at 4 and negative 0.7? Okay, so there's 4. That's technically 0 because it's so small. What's happening with my original function at 0? Oh, it looks like I have a minimum point there, and over here at my negative 0.7 I have a maximum point in my original function. Keep in mind what derivatives mean. Derivatives mean velocity. Well, at a maximum or a minimum, are you increasing or decreasing? You're not increasing or decreasing. You're not changing necessarily. You have no velocity. So that's why the velocity function or your derivative is 0 whenever you have a max or a min in the original graph. That is a key point to derivative, is that your original function has a maximum or a minimum point for your derivative. Maybe we'll even put velocity in parentheses there, equals 0. Okay, so two key things we're starting to recognize about graphs is that the derivative looks like it's 1 degree less. It also looks like your derivative will be negative where your original is decreasing, and it'll probably be positive where your original is increasing, which I bet you if we look at it, when my function changes from decreasing to increasing, oh sorry, that's not the best graph. When my function changes from decreasing to increasing, that's when my derivative switches from negative values to positive values. So yeah, that tends to be true there. And then with this function, or this part D here, the other thing that we wanted to point out is wherever your derivative is 0, your original has maxes or mins. And it goes both ways. If your original function has max or mins, then you know your derivative is 0 at those same x values. Okay, so we're going to plot g of x equals f of x plus 10. Okay, so f of x, that was under y1. So I'm going to go back to y bars. Oops. y1 plus 10. And then we're going to plot g prime of x. So we're going to do n deriv. But now I want y3, because that's my g of x. So comma x, comma x. How is the graph of g related to the graph of f? Okay, so here we go. Let's make these maybe a little different. Okay. There's my first two. Oh, you know what? Let's make that. There we go. Okay, so there's my original y sub 1. There's my derivative. g of x, and there's my g prime. Now, all we did to find g of x is we added 10. All that does really is shifts the whole graph up 10 units. And you can see it didn't affect the derivative at all. Well, that's because since it has the same shape, at any point here you're having the same speed. Or like if we were to look at here, you still have the same minimum, like you still have a minimum point at that x value of 4. So the speed or the derivative value should still be 0. The speed here at this point is going to be the same as the speed on f of x because it has the same shape. So yeah, the derivative for both of those end up being the same. Alright, so we would say first that g of x is the same as f of x, just shifted up, shifted up 10. Okay, the next thing, graphs of f prime and g prime are exactly the same. The reason for that being f and g are changing at the same rates. Okay, let me flip here to the next page and see what we got. Okay, for this one, we might hold off on that one because when we practice this tomorrow, it might be good for me to go through this with you guys and then you immediately practice afterwards with some graphs. But just to give you a picture of what this is going to look like, the figure below shows the graph of the function f defined for an open interval. On the same set of axes, you're supposed to sketch the graph of the derivative function and describe our process. We're going to be using some of the key things that we pointed out here. So I'd make sure before tomorrow, and maybe even right now, that you go through and review some of the connections that we made between the derivative graph